Okay, so for our first problem, we're looking at a figure skater. The figure skater starts with his arms outstretched, and then he brings them into his body. So we're looking at conservation of momentum here. So when he has his arms outstretched, he has a different mass moment of inertia than he does when he brings his arms in. So in the initial case for the mass moment of inertia, according to this problem, so the outstretched arms, we measure it as like this is a slender rod, right, with an axis here. So we have the mass moment of inertia for the person, and then we have an additional mass moment of inertia of the arms, just this rod, basically making a T shape here, okay? So it's the initial is ICM plus I rod, okay? And then for the final mass moment of inertia, we have the ICM of the man, and then we add an additional ICM for like this hollow cylinder. So we're basically considering his arms like this wrapped around cylinder added to the shape here. Okay, so we're given this ICM value, this like constant ICM value of 0.40 kilograms meters squared. Then we're also given, so the mass of his hands and arms, so hands and arms is equal to 8 kilograms, okay? And then we're given like the radius of both. So like when outstretched, so the total span is, so let's say radius of hands and arms is equal to 1.8 over 2, right? And then, let's see, and then for the internal part, for when they're wrapped, so radius of hands and arms, like in, like when he brings them into his body, is 25 centimeters. And then, yeah, I think that's everything that we're given here, right? We see this constant angular speed. We have the mass of his hands and arms, the total mass, and then we have the changing radius for both of these. So, yes, all right. So we know that our angular momentum, so we have Li is equal to Lf, right? So the general expression for this, we have Li is equal to initial angular acceleration times initial mass moment of inertia, and then Lf is equal to final angular, did I say acceleration? Sorry, angular velocity, W's velocity times final mass moment of inertia. Okay, so we're given the original angular speed, so this is this Wi here. Okay, so we do have that. So we have this Wi, right? And then we were given the pieces that we need to solve for this guy, and then we're asked to find Wf. So Wf is our goal here. So we want to know what is this final angular speed. So we're trying to solve for this Wf. Okay, so we're going to set up and solve for these pieces, II and IF. Then we're going to plug in our Wi, and then we're just going to do some algebra to solve for Wf, okay? So our final answer, if we know that the, if we know that the initial, right, is equal to the final angular momentum, we know that Wi, right, mass moment of inertia I is equal to Wf, mass moment of inertia final. So Wi times the initial divided by final is just going to give us our Wf value, right? So all we need to do is just solve for our pieces, and then we're going to do this, right? This is how we're going to get our final results, okay? So let's go ahead and take what we have, and we're going to solve for our pieces, okay? All right, so I kind of wrote this out here. I thought that would just, sorry, point, but we'll highlight. Okay, so for the first one, like I talked about up here, right, we have this, I can copy these and bring them down so I don't have to keep scrolling and giving you guys kind of vertigo here. Okay, so for our initial, right, we have this ICM is, the initial is equal to this constant that we're given for both of them, right? This is the ICM for both of them, right? It's just like this constant mass moment of inertia of the human person. Okay, and then we're adding this I rod. So the rod is his arms, right? So it's like a rod that's pivoting at about the center, this extra rod, and this is its center, right? And it's spinning around this way, right? And then we have the person, right? Okay, so this is the general equation, right? For I rod, we know that it's equal to, oh, I don't know if I wrote that out. So I rod is equal to 1/12 mr squared. That's for I rod. And then I cylinder, right, is equal to mr squared. Okay. So what we did for both of these, right, was we took that initial constant that we were given, constant for ICM for the human, and then we added 1/12, and then we have 0.8 or 8.0 kilograms. What did I say? They span 1.8 when wrapped. Is that correct? Do we need the, oh, I'm sorry. The general r squared, ml squared, is it the total length of the rod? This might be a typo on behalf of their problem. That's what they have in their solution. We will go ahead and solve it that way. But somebody check me on this, because L might be the total length of the rod here. Okay, I thought that this was R. Okay, anyways. So we solve for II and we solve for IF. So let's look at what those final values would be according to this problem. I'll come back and fact check this guy later and report back to you guys. So II, just based off of what they have for this problem, 2.56 kilogram meter squared. And then IF is going to be equal to 0.90 kilogram meters squared. Okay, so we have both of these. Fantastic. Okay, so that's basically our whole problem, right? So once we have both of these, what we decided that we needed to do, right, was that we needed to plug it in, okay? Just the ratio of those times our initial velocity that we were given, angular velocity. So we were given the initial angular velocity is equal to, what was it in this problem? Here we go, 0.40 revolutions per second. So 0.40 revolutions per second. And if we plug that in with the ratio, so if we plug in our WI, right, if we plug in this, is equal, or sorry, not equal to, is multiplied by II over IF. Our final angular velocity that we're going to get for this problem will be 1.14 revolutions per second. Okay, so pretty, not too bad here. Somebody fact check me on this one. Okay, mr squared for the rod. Is it mr or is it L? Because from this problem statement, if they say they span, that would be like the diameter, right? If they span, that would be like, this is one hand, right? And then this is the other hand, right? So this would be 1.8 meters. But anyways, okay, so the takeaway for this one, we have the initial angular momentum is just equal to the final because it's conserved. There's nothing that's taking energy away or momentum away. And we are just converting it, right? And we're going to end up with more this increase in kinetic energy, right? Because we know that kinetic energy is equal to this equals I times W squared, right? So in the end, when we have a larger, if WF is rising here at the end, so, well, yeah. So yeah, W increases and L is constant. So kinetic energy will increase. So the increase in kinetic energy comes from the work done by the skater when he pulls his arms in. So this person is going to be moving faster because this person does work by pulling his arms in. And so therefore we increase the kinetic energy of the system. Okay, so just a conceptual takeaway there. Okay, so that's this one. I'm going to go ahead and pause this one and then we're going to move on to the next problem.